Okay, good morning, everyone. Welcome to VSPG. This week we have a presentation by Professor Nora Noffke from Old Dominion University. The talk is titled A Fossil Microbial Ecosystem in the 3.48 billion-year-old Dresser Formation, Pilbara, Western Australia. Next week we'll have Sebastian Fisher from the University of St. Andrews presenting about the Lewisian gneiss, still pending a title, but we will have that. I will be sending out an announcement about that tomorrow. Andre, do you have any announcements today?
Maybe you can mention that change in the talk for June, I think 2nd.
Oh.
Christoph Herbig will be talking to us.
Yeah, in 2 weeks, Christoph Hubeck will be talking his presentation, 8 ICDP boreholes and 3 tunnels through 3.7 kilometers Paleoarchean shallow water strata investigating the setting of early life. So that was a last minute change in the schedule. So go ahead and check the schedule to keep up to date. With that, I'll go ahead and I will introduce Nora for us today. Nora, you can go ahead and unmute yourself and start sharing your screen, and I'll give you the cue. So Professor Nora Noffke is an interdisciplinary sedimentologist integrating aspects of microbiology, geochemistry, paleontology, and mineralogy into her work. Her research has focused on biofilms and microbial mats in clastic sedimentology and investigating complex interactions between macroscopic organisms and biofilms and their imprint on the sedimentary rock that hosts them. She completed her bachelor's and master's at the University of Tübingen in Germany and her PhD at the University of Oldenburg in Germany, studying the geobiology of marine environments. Today, she works as an associate professor at the Old Dominion University and as a visiting scholar with the Carnegie Institute in Washington, D.C. The 3.48 Dresser Formation hosts some of the oldest biogenic structures on Earth, and Nora will be presenting today about microbially induced sedimentary structures from these rocks. Thank you, Nora. Please take it away.
Okay, good. Yeah. So thank you very much for the invitation. Before I start, I'd like to thank you, Alex and Andre, for organizing this entire seminar. I think it's awesome. And I know it's a lot of work. So thank you for doing that. Here is my talk. I like to talk about the ancient microbial ecosystem in the Dresser Formation in the Pilbara block, Australia. That is work that I conducted together with David Wasey and Bob Hazen, who contributed all the geochemical and biochemical measurements. So what I like to do is, oh, does it work now? No? Yes.
Yeah, that's good.
Yeah, okay. So first I like to talk about biofilms, microbial mats in modern settings, how they form sedimentary structures that are very, very characteristic. Those structures occur in clastic settings, not in carbonate settings and so forth, where we have very early mineral precipitation taking place. So I'd like to talk about a little bit how those biofilms look like, how mats form, and then how they induce those very, very characteristic structures. In order to do so, I like to elucidate the interaction of benthic cyanobacteria with physical sediment dynamics, which includes erosion and deposition of sediment. And then finally, I like to plunge into the Dresser Formation itself. So we move to the Pilbara, where we have a nice rock succession that records an ancient coastal sabkha. There's a tidal influence visible, and the entire environment is overprint by volcanic activity, volcanic influence as well. Here I like to show a succession of microbial structures along a transect from shallow shoal area across a tidal flat to an area which most of the time was exposed subaerially. So let's take a look at biofilms and microbial mats, what those actually are. This is a view into a modern tidal flat. It's the North Sea in Germany, the coast. We get the impression by just taking a look at this photo that those sediments are actually composed only of quartz sand grains. However, if we take a magnifier, we see that those sediments actually are widely colonized by a great variety of benthic microorganisms, of which in the modern cyanobacteria play a big role. They're very, very common. There are two examples that occur worldwide. One is Merismopedia punctata. It is a form that is characterized by coccoid cells, round-shaped cells that form those pillow-like clusters here attached with their extracellular polymeric substances, the EPS, which are slimes, to a solid surface. Here you see Microcoleus tonoplastis. It was recently renamed. I still use this name here because it's very common in the literature still, which is a filamentous organism forming bundles that resemble a little bit like spaghetti in a bag. Now, initially, when cyanobacteria start to colonize a sandy surface in an aquatic setting, they form biofilms around each individual grain. So here you see the surface of a quartz grain, and you see how this quartz grain is enveloped by this organic biofilm. Biofilms are associations of microbial cells. Here you see one. In this case, it's a diatom. It doesn't matter. It's a modern biofilm. So there are eukaryotes in this biofilm. But you also see quite nicely those EPS, those adhesive mucilages that allow those microorganisms to attach to solid surfaces. Now, over time, such biofilms continue to grow, and in the end, large-scale microbial mats can cover sedimentary surfaces. So that's what you see here. It's a modern microbial mat from Tunisia. It's about 1 centimeter thick. Here's a knife for scale. Nice blue-green color, which means there are cyanobacteria predominant in this microbial mat. And clearly, if we take a look at this photo here, we can already see that such a microbial mat must affect sedimentary processes in a clastic setting. Now, microbial mats affect sedimentary dynamics in certain ways. We know that it's very well studied for chemical settings where microbiolites form, such as stromatolites, but in physical sedimentary settings where only erosion, deposition of sediment takes place, no real depositional precipitation of minerals, there we have the formation of microbially induced sedimentary structures, abbreviated as MISS. So here you see a photo of one type of MISS, and I think many people really are not too familiar with those structures. So I like to show a couple of examples so that you warm up a little bit to the morphologies characteristic of those structures. So here, multidirectional ripple marks, an example from the modern. You see a tidal surface here. It's all composed of sand, but you see that here are two ripple crest directions occurring. So one direction is from left to right, so to speak, which is here. Another ripple direction is in this direction here. Here is a patch that shows this other ripple mark direction. Here's another patch, and here's another patch. Here's a knife for scale about 25 centimeters in length. Now, such a multi-directional ripple mark pattern that we see here in the modern is displayed here on a sandstone surface in the Pongola supergroup. It's 2.9 billion years old in South Africa. So those structures record very, very well in the fossil record. Another example, polygonal oscillation cracks. Here you see a microbial mat surface. The scale is about 25 centimeters. Here you see a microbial mat patch, a polygon. I'm lining this out here with my arrow. Here's another polygon, and here's another one. Those polygons are characterized by edges that are a little bit elevated. So there's a ridge here all along the polygon edge. And those ridges show where there are cracks in between those polygons. Those cracks are regrown, overgrown by a younger generation of microbial mat. But you see that the cracks are lined by two parallel running ridges that we can see very nicely here in this fossil example from the Pongola supergroup. Then we have erosional remnants and pockets. Here, a modern example that you've just seen. Scale is about 1 meter. This MISS is characterized by planar surface parts. This is where microbial mat is fossil. It's a lithified microbial mat, but formerly, before lithification, erosion eroded away microbial mat, and those erosional pockets formed, which you see here, filled by water. Here, the sand beneath the microbial mat was exposed and could be ripple marked. Microbial mat chips are just simple centimeter scale fragments of microbial mat here distributed at random on a modern sedimentary surface, and here a fossil example again from the Pongola supergroup in South Africa. So that was just a few examples of MISS so that you can get an idea what I'm talking about. You see that MISS do not resemble stromatolites at all. So how do they form? Let's take a look at the interaction of microorganisms with physical sediment dynamics. So first of all, in general, this is how the zones of a tidal flat look like. There is the subtidal, which is almost always covered by water. It must not be deep. It can be just a few centimeters deep. Then there is the intertidal zone, which is the zone affected by the hourly or daily tides. So the flood current, which is ascending, and the ebb current, which is descending. And then there is the suprotidal zone, most of the time subaerially exposed. The lower supratidal zone might be covered by water during strong storms or very, very high spring floods. So how do cyanobacteria respond to sediment dynamics? Here you see a graph which where you can see 3 arrows. This arrow here indicates intensity of erosion and defines this field of erosion here. This arrow indicates the increase of deposition, intensity of deposition, which defines this area here, the field of deposition. And then there is a third arrow, which is latency. Latency means that's the time period during which neither erosion nor deposition of sediment takes place. Those rectangles that you see here show how different types of microbial communities react to specific dynamic conditions. And I'm going to talk about this very briefly. So let's take a look at what happens with a biofilm or microbial mat in times of stasis where there's no erosion or deposition of sediment taking place. What we can observe are two things. First of all, binding. Binding, that's a close-up here. It's a close-up onto a microbial mat fabrics. Binding means if we take a close look at a biofilm that now has time to organize, to mature, what we see is that filaments of cyanobacteria move actively through the sediment to establish a position suitable for interaction metabolically with their neighbors. So it's an active reorganization process. And by that, the biofilm can add new members, new constituents, and so forth. So a microbial mat fabrics can form, which of course takes some time. But we also can then observe growth, which is biomass enrichment by biomass production. Here's a vertical cut through the sediment. We see ripple marks here. And we see that the biofilm actually now is a microbial mat. It's about a centimeter thick here in the ripple valley. A planar surface is forming over time, and that's why we call this process of binding and growth with respect to the structures that result as leveling. Various latencies cause different types of mat colonization. In the intertidal zone, the lower intertidal zone, there's constantly water motion. Biofilms are forming. Here you see a Merismopedia punctata filling in pore spaces. Endobenthic microbial mats form in the upper intertidal zone. Those are mats that can actually form literally within hours. And then epibenthic microbial mats. Those are the textbook mats that we find in the lower supratidal zone, where you'll see they cover ripple marks completely. We don't see anything of the preceding surface anymore. So what happens during erosion? What we see is that cyanobacteria react by biostabilization. This is a close-up view, lateral view onto a microbial mat. You may think I'm not able to take a photo so we can see the filaments in focus. That's not my fault. The reason for this blurry appearance is that the filaments are embedded in EPS, in those mucilages that glue sedimentary grains together. You do not even see the quartz grains here anymore, but we also can visualize that the grains are entangled by the filaments, and both processes, this mechanical entanglement and the adhesive mucilages, increase the resistance of the surface against erosion significantly. We measured biostabilization effects of different microbial mat types in the field with this flume chamber here. So now the question is, what happens during deposition of sediment? What we can observe, again, that's the same microbial mat that you've just seen. It's a close-up, a lateral view, and you see sedimentary grains raining down, so to speak, onto the mat surface, and the microbes react by orienting perpendicularly. All the microbial mat is moving upward and actively and incorporates the newly deposited grains into the microbial mat fabrics. That's what we call baffling and trapping. All those microbial reactions to sedimentary processes, to the dynamics, cause, so to speak, traces in the sediment, traces caused by this entire microbial mat, not by the individual filaments. And those traces are called microbially induced sedimentary structures. There are 17 main types. Some types can be related to one specific microbial activity. Other types result from an overlap of microbial activities over time. MISS occur through the entire Earth history. We know them from all aquatic deposits since the Archean. This is in German, it doesn't matter, you understand this anyway. Shelf means shelf, littoral means littoral, terrestrial means terrestrial. So you see, there's a nice record of MISS in aquatic deposits for the entire Earth history. Nicely, we can observe and monitor the formation of MISS in the modern. So we have data on the distribution, on formation processes that we can use to understand Archean fossil microbial mats. So let's take a look at these. Let's move to the Dresser Formation. The Dresser Formation crops out in the Pilbara block in Western Australia. It's part of the tectonic structure called North Pole Dome, an area which is long known for hosting a lot of excellently preserved fossils. Think of microfossils in chert, think of stromatolites and so forth. So there's a whole wealth of evidence that life was pulsing at 3.48 billion years ago already. So the Dresser Formation has an age of 3.48. There's a typo here, so 3.48 billion years. It's a little bit older than the Mount Ada and Duffer formations, the Marble Bar Chert and so forth. All those formations very famous because they constitute the Varaguna group, which is known for its significance to understand early life. The Dresser Formation records a paleoenvironment that's characterized by an ocean, which is commonly not recorded, but there are signs that there was a shoal bar. I'll get back to that in a moment on the composition. There was a tidal zone, a tidal flat, a sand flat that was cut through by very shallow tidal channels. We have ripple marks in those sandy sediments. There were tidal pools that from time to time dried out completely, but they kept water also for a long time. And then there were areas that were submerged subaerially, where we have a more intense evaporation going on. So while there is a significant volcanic influence visible in those deposits, the paleoenvironment can be compared with a modern tidal sabkha that we know from modern Tunisia. So here you see a sand flat, there are very shallow tidal channels, there are some tidal pools that sometimes dry out completely, and there is an area that most of the time is subaerially exposed, and there where evaporation can take place, and sometimes a lagoon might form temporarily in such settings. So there are different types of microbial structures in those different types of paleo environments. First, there is a shoal bar, which all this paleo environment was described by Buick and Dunlop already. So there are shoals that show ooids. So this is a carbonate deposit in this otherwise mostly clastic succession, evaporated clastic succession, ooids that record there was a shoal bar, a very shallow shoal bar at some point that separated the main tidal sabkha from a more active setting of a very early ocean. Then there are tidal channels where we can find little stromatolites that were described by Van Kronendonk et al. 2006, amongst other publications. So very simple stromatolites in a deposit that includes some carbonate. And if we take a look at thin sections through ripple marks, in such tidal channels, or at the wall of those tidal channels, we see some biofilms here, nicely preserved as carbonate matter. The biofilms were covering the ripple surfaces, but there were also rhythmically overgrown deposits that over time were filling in the ripple valleys. So we see nice biofilms that were forming here. We call something like that, it's an MISS, it's called sinoidal structure, which are basically microbial drapes that cover ripple crests and ripple valleys. You've seen one before when I talked about leveling in of a ripple valley in a modern setting. This is a close-up here, so we see little, not real tufts, but little triangular features here, very, very small. There are some fossil gas bubbles preserved as well. In overall, there's a nice carbon here. David Wasey did some analysis on the composition of this material. So there's carbon, there's pyrite, and the carbon has a biological signal. Let's move out of those tidal channels onto the slightly more elevated sandy parts of the tidal flats. That's the intertidal zone here. We see thicker microbial mats. Here you see, I start with this one here. It's a microbial mat. We take a look from downward. So think of you're standing on a sandy surface covered by a microbial mat, and you look down onto your toes. You don't see your toes, they would be here somewhere. But what you see is here the microbial mat, nice and thick. And you see here a little microbial mat chip, a fragment that once was attached to the mother microbial mat, so to speak. Here's the edge of the microbial mat. It was attached here, but now it's ripped off and it was redeposited right away. This is about 2.5, 3 centimeters in diameter here. Here's another mat chip. Here's another one. Here's another one. And the same situation we see here in the fossil, in the Dresser Formation. This is a fossil microbial mat. How we know that, I show in a moment. So here is sand. Here's a microbial mat. Here the microbial mat was eroded away. So you see the edge of the microbial mat. So that's basically this line here. And here you see a microbial mat patch, a little chip, a fragment. That was originally here. Now it was eroded and redeposited right away. Here's a chip that was deposited atop of a microbial mat. So it's a very, very similar situation, a small edge of a fossil erosional remnant and pocket, which is an MISS very characteristic for sandy tidal flats. Another thing we can see here are wrinkle structures. That's a term for anything that's wrinkled in a classic setting. We don't need to bother right now with formation. There are microbial wrinkle structures. Here a modern example, wrinkles that formed in a modern microbial mat due to various processes. So that's what we see in the Dresser Formation as well. Now, if we cut through a fossil microbial mat like this one here, and we take a thin section, what we see are features like microbial mat fabrics, textures of filaments, that have a high carbon signal. This is basically a thin section here, and you see similar textures from a modern microbial mat. You see here the filaments, this white material is fossil EPS, and here individual grains that float inside this mat fabrics. The grains you see here, it's not the best photo in the world, but here's one, here's one. So very, very similar mat textures that we see under the microscope. And again, David did an awesome job in analyzing those textures And we can see that there is carbon with a biological signal in those filament-like textures. Now let's move into the tidal pools that were just a few centimeters deep as the modern ones, also in modern Tunisia. What you see here, and I like to start with this photo to make it a little bit clearer, are polygonal oscillation cracks. That's a slightly different photo than what you've seen before. Here you see a polygon of a mat, here in a modern microbial mat. Here's another one. Here's another one, another one, another one. Those polygons are separated by cracks, and I'm lining one crack out here. So you see, there is a flat area here. It looks more like a large groove. That's a crack which is overgrown by microbial mat again here. And here's a ridge, which is the corner of this polygon. Here's a ridge on this side, which is a corner of this polygon. And here's another ridge, which is the side of this polygon here. So how do polygonal oscillation cracks form? It's a very strange name. Sorry, we didn't come up with a better term here. If a microbial mat in a pool dries out because the water desiccates, so the pool desiccates, it's drying out. So the microbial mat desiccates, the mat cracks. You have normal desiccation cracks forming in the mat. Each polygon is shrinking and moves laterally. It forms a smaller polygon. If the tidal pool is filled with water again, the microbial mat gathers water and the polygon is expanding laterally again. If it desiccates again, then those polygons shrink again. So it's the polygons basically change shape from smaller to bigger. It goes back and forth, back and forth. But of course, that takes time. And the microbial mat continuously grows. As soon as the tidal pool is filled with water, the crack that was formed in the very first microbial mat generation, it is overgrown by a younger generation of microbial mat again. Then that mat cracks because it's dried out again, and the whole process repeats over and over again. So that's how those polygonal oscillation cracks form, and that's what we see here in the fossil. Here you see a polygon here. Here's another one. Here's another one, and another one, and another one. What you see nicely and even much better preserved, for a reason I get back in a moment, is this area here. That is basically the crack. Here's a ridge, here's a ridge. This is the crack that was overgrown again by a younger generation of microbial mat. So exactly this here. This here in the modern is what you see here. Now, it would be nice, even if in the modern, if we would see those polygons quite nicely. In a way, you still see it. The reason why they're a little bit distorted is that if the microbial mat dries out, there are gas domes forming beneath each individual polygon. Those gas domes rise up, not very high, a few centimeters at most, half a centimeter, 2 centimeters, until the mat is so dry it cannot withstand the gas pressure, which is increasing underneath the microbial mat. So the gas dome ruptures. There's this very impolitely smelling gas is escaping, and the gas dome is collapsing again. And where the gas escapes, a small hole remains. And this is what you see here. Those are the holes. So here were gas domes in each center of the polygon, and the gas domes ruptured, and those holes are now visible on the surface. So this is what we see here. Now, if a microbial mat is healthy, it's covered by water in a tidal pool, what we very often see are tufts, little triangular elevations that are formed by active migration of filaments. They glide along each other. They form little millimeter high tufts, sometimes ridges that form those honeycomb patterns here. We compared the morphology of those honeycombs with the modern, the height of the tufts, and we did some statistics. It's exactly the same. So something like that we can find in the fossil in the Dresser Formation. In the lagoonal sediments, which are nicely exposed in a specific site there in the Dresser Formation, we can see Biolaminites, so nice layers enriched with more carbonaceous matter that resemble Biolaminites. So there are light colored layers, which is predominantly sediment. This is typical for Biolaminites. It's a vertical section through a microbial mat. So you see here sediment layers, very, very small scale. Sediment layers that alternate with biofilm layers, which are obviously the darker layers. So this is what you see. How do we know that those was former biofilm here or microbial mat? Because we find on the surfaces of such layers where they crop out centimeter scale microbial mat chips. Here, those are microbial fragments, very characteristic, those lobes and embayments that you see here. This is a former microbial mat surface here. You see the mat chips were actually originally deposited top down, meaning we see the sand or the sedimentary lower unit of the microbial mat. So the microbes itself, the microbial layer is pointing downward. We don't see it. That's a modern example here. This is sediment here. This is a microbial mat surface. So this here is the same like that, the darker surface part here. And you see here microbial mat chip pointing where the surface is covered. So that chip is top down, another top down chip, another one. This one here is top up on the sand, top up, and so forth. So this is what you see in the Dresser Formation. Another example here, top down. No, this is top up but dried out. Yeah, top up, dried out. Top down, dried out. Top up, dried out. But here the microbial mat surface. So here the microbial mat chips, this one is a little bit folded over, and here the same from the Dresser Formation. Here, those chips forming a little pile here, just like here, you know, those are overlapped. Another one here, which could be something like this. This is what we see quite nicely in the Dresser Formation. Vertical section through those chips shows their internal build up. So we have laminae, carbonaceous laminae in the chips. Here's one little one, which is actually rolled up, which shows that chip was rolled up. I sketched it here too, so you see it a little bit better. And then David did those awesome analyses here of the composition of the formerly organic layers in those chips. So conclusions, we know that Dresser Formation is the oldest non-metamorphosed sedimentary unit in the rock record. It records a coastal sabkha environment that more or less corresponds to a modern coastal sabkha like in Tunisia, for instance. We have to consider the volcanic influence, of course, in the Dresser time. But we saw MISS that in morphology correspond to MISS that we know from the modern in very similar settings. And that applies to macroscopic morphologies as well as morphologies that we see in thin sections or textures. And those similarities suggest that there was a microbial ecosystem around in the Dresser Formation at that time that if we use modern MISS, we can say, well, the modern microbial ecosystem may serve as a model for those microbial mats in the Archean. One can go now debate, were those cyanobacteria already or not? I always say yes, they were, but it's a very ancient type of cyanobacteria. I believe that they were photoautotroph, but that is a completely different part of discussion. So that's what I presented here. It was published in 2013 in Astrobiology. It's an open access article. If you would read about this, you have access. It's free. It's on the internet. And if you like to know more about MISS, I wrote a textbook about that in 2010. You don't need to buy that book, but you should definitely read it if you are interested in MISS in clastic settings through the fossil record. And with that, thank you very much. I am happy to answer any questions.
Thank you, Nora. Great. People will start sending the questions. I do have one, and that was sent during the presentation to me as a direct message from Kaysunder Sarwan. Does the microbial composition of the biofilms at subtidal depths change along the transition to intertidal endobenthic mats and supratidal epibenthic mats? Is this composition also subject to change temporally and periodically?
That's a very good question. So the composition between biofilms that colonize lower areas is different than the composition of epibenthic microbial mats. So I always call that something like that a biofilm catena. So similar, like we have different soils forming in a terrestrial settings with respect to availability of water and nutrients and so forth, depending on the geomorphology. We see that in the marine or aquatic setting as well. So we have very simple biofilms in the lower parts, but the longer time the communities have to grow, the more constituents assemble in the microbial mat. So there are different types of microbes assembling. Also, the dominance of certain other species, so to speak, is changing. And if we go into the epibenthic microbial mats, there's a change again. So at that time, when I worked on the North Sea area, that's 20 years ago, we had in the biofilms dominance of Merismopedia punctata. In the intertidal, the endobenthic microbial mats, a dominance of Oscillatoria limosa, which is an organism that can move very quickly through the sediment to form a microbial mat fabrics, very fast, within hours. And then in the epibenthic microbial mat, we have a predominance of Microcoelius tonoplastis, which excretes a lot of mucilages that is resistant against the long periods of subaerial exposure in this zone. So there is a change in composition and also an increase in diversity.
Okay, we have a question from Rachel Serpena. Her hand is raised, so go ahead and unmute yourself.
Yeah, thanks, Alex. Hi, Nora, great talk. I am one of Mary Drizer's PhD students, and I was just wondering about, in your images of the fossilized mat chips, there seems to be a color difference between the mat chips and the preserved mat itself. And I was just wondering if you could speak to whether this was a weathering difference or if you saw a compositional difference between the in situ mat and the mat chips. Thanks.
We go back here. So this one here.
I was actually referring to the 141. Yeah.
This one?
Yeah.
Yeah. Okay, good. So here, what you see here is that's basically the sandy layer underneath the microbial mat. This one here. So if you cut vertically through here, what you see is, let me go. Where is it? So see this here. This is a typical composition of a microbial mat chip. So the top is the microbial mat itself, or the carbon and so forth. Now here in this fossil example, this layer here is sediment. It's underneath. They are both layers are always attached. That's very typical for a microbial mat chip. So you don't have just an organic layer that peels off independently from the sediment. It's always both of them together. And the reason for that is that here there was originally microbial mat. But if this sediment here is covered, buried by freshly incoming sediment, then those microbes migrate upward, but they leave all the mucilages behind. They glue the sediment together. That remains. They're very, very robust. They don't oxidize or anything that quickly. And then the organisms assemble on top again, form a new microbial mat. This one here had nice time. There was not much influence. There was here a time where there's a little bit more deposition of sediment recorded. But here you have then the real nice microbial mat establishing. So this is what you see. This has nothing to do with weathering. It's just the way how the chips are composed. Okay.
Right, thank you. Sorry, I think I just misinterpreted your image on this slide. Is the top left image a modern picture?
Which one? This one?
The top left, yes.
Now I know what you mean. So this is a modern one, obviously.
Okay.
So what you see here, this dark, yeah. So in this case here, this is from Portsmouth Island here in North Carolina, one of the barrier islands that we see here. Here, the sediment includes a little bit more clay. That means we have underneath the cyanobacterial layer, the first of all, there is oxygenic cyanobacteria, then anoxygenic cyanobacteria, and then there are sulfur reducers and methylogenic bacteria. I hope I said this correctly. Once a microbial mat chip turns over, what you see here, this dark part, is basically the layer of the sulfur reducers. And that's this stinky part. That gives this foul smell. If you turn a microbial mat over, it smells impolitely. So it's not oxidation. And it's quite nice that actually you mentioned that, because sulfur reducing bacteria were shown for the Dresser formation. Pascal, Philippot, and others showed that there is a nice sulfur isotope signal, and I think Dave Wasey as well, that shows that the sulfur reduces around already. Okay.
Great, thank you.
All right, I have one in the chat from Morrison Nolan. When collecting SEM pictures, what sample processing do you do on the mats? Do you carbon coat them?
So is it now the fossil or modern ones? It doesn't matter.
Morrison.
Yeah.
Okay.
So in any case, so we don't carbon code for the reason obvious that if you carbon code, you get a signal that interferes with your measurements. So this is all gosh, what was this, aluminium something or platinum, one of both, either way.
Thanks, Morrison. Okay, the next question is from Frances, but Frances has her hand raised, so I think she'd like to ask it herself.
Yes, thank you very much. Thank you for a lovely talk, Nora. It's always very edifying to listen to your talks and learn. I have a little bit of a problem with your interpretation of the organisms that formed these mats as cyanobacteria. I agree that there were probably phototrophic organisms, but the environment just indicates anoxia. So I think perhaps you can't really talk about cyanobacteria, but they're very definitely anoxygenic phototrophs.
Yeah, so I really like to keep out of that discussion. I'm just a stupid sedimentologist. My background is ice fossils. Whether those are cyanobacteria or anoxygenic or something, I really don't care. I leave this really open. If someone says those are or not, I'm fine with anything. What I'm fascinated by is very simple. The morphologies of the MISS, that they are out there, that they are so similar. I have way more photos, fresh photos actually, that I took from the field. And that's what I find fascinating. So we had microbial mats that, with respect to mechanics, reacted the same way to physical sediment dynamics like the one in the modern. And being plain in the head, I say, well, you know, if the moderns are made by cyanobacteria, then something like cyanobacteria might have been around at that time. But really, you know, whether those are cyanobacteria in the dresser or not, that probably is for the future research to document.
Well, I think there's been a lot of work done that's documented anoxygenic environments. So definitely, you know, phototrophs, but highly unlikely cyanobacteria. But
yeah. It can be just something like Veggiator. That's very common in modern microbial mats, which is actually an oscillatoria limosa, so to speak, but it lost its photosystem too. So it's just doing anoxygenic photosynthesis. It's I'm very happy with that. Yeah.
Thanks a lot.
Okay, at this point, we don't have any more questions open in the chat. If anybody would like to just open discussion, feel free.
Hi, Nora. Good question. Good talk. I'm just wondering, in one of your slides, you showed this repap of microbial mat, but with a scale around 2 microns or something, and the upper part of it looked like dark, probably organic rich. And I didn't get it, but maybe it was from the dress formation. I'm not sure.
This one?
Yeah.
Yeah. Yes.
Yeah.
So that is basically one of those here. Here, this one. So it's from the dresser, and yeah. So this is shown. Yeah.
And considering this scale, I'm wondering if anyone tried to study heterogeneity in terms of sulfurocarbon isotopes to actually address this question in terms of metabolism, but also in terms of layering, that as in modern mats, you can see the top to be whatever cyanobacteria, and when you have methanotrophs, methanogens like sulfate reduces. So with this scale, can you see this indication of this sort of layered microbial community?
So I don't know of anyone who has done that. That's for either for the future to do, or I just haven't seen it. I was ill for a few years, and I'm still picking up literature left and right. So yeah, I think it's possible. Oh, I think so. Yeah.
Thank you.
Okay, Chris, you like to unmute yourself?
My turn?
Yes, go.
Yeah, hi Nora. You showed us quite a number of comparisons between recent myths and outcrop photographs, which mostly were from the Dresser Formation. How do you, and you interpreted the latter, that is these outcrop photographs, as reflecting weathering patterns of the Archean, expressing the morphology of the myths. How do you know that these outcrop surfaces in the Dresser are not a result of recent, let's say, Holocene weathering? You interpret them as reflecting Archean morphologies.
Okay, good. So that is an excellent question. And I actually, something like this, I actually wrote an entire article about that, which came out in Astrobiology last year, 2021. Again, it's open access. It's a tremendous long article. So you might want to read that. In that article, I explore different types of bedding planes. So we can have erosional bedding planes, like formed by amalgamation or syndepositional erosion, and so forth. And then there are bedding planes that record the original environmental surface. Now, those bedding planes are the ones that are of interest for us. So bedding planes that originally was a environmental surface where the microbial mats had time to develop. And if a microbial mat stabilizes the sediment and baffles and traps actively a certain size, a population of grains, that contributes to the preservation potential of such a surface. So if we take a look at that, those surfaces here are the original environmental surface. But what was I going to say? The original environmental surface, but it was exhumed by modern weathering processes, which of course you need to have to see any surface in outcrop, right? If you have no, where is this other photo here? Where do I have this now? Where is it? This one? Yes. So if you have a vertical succession like this here, layer, 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 without modern weathering, you don't have exhumation of surfaces, right? And then you see that surface, then you have to decide, you're absolutely correct, was this an erosive surface or was it a depositional one? Well, we can distinguish because we don't look at the surfaces just like macroscopically. Here, where is it? We do our homework, we do thin sections, and then we see where fossil microbial mat was. And that means it was an environmental surface, not an erosive one.
Thank you.
I might have missed the explanation by Frances, and maybe she left now, but why she thinks it cannot be cyanobacteria.
Yeah, so I'm on the left foot there. I know that there is a little bit resistance in the community to say early Archean cyanobacteria. No, it isn't. If I take a look at this here, right, this here, if it were cyanobacteria in the modern sense, like this one here, where is it? Now I have to find it very quickly. This one, no, one more. This one, no, Jesus. Where are they? Here. So yeah, that's a modern cyanobacterium. This is very big. This is 250 micron in length. Microchloris tonoplastis was called blue-green algae originally, or blue algae, something like that. In the older literature, you know the word algal mat, because people thought formerly those are algae, not cyanobacteria. Was until 76 until people realized, no, those are real microorganisms. They're just very big. Now those are big. I don't really see that in a thin section like this here. I would see it. There's another example here. That, yeah, I see it here a little bit. So if one would go with morphology, which one should not really do in the microbial world, I know that, I would say, well, not each type of microbial mat that we see in the dresser formation shows filament type things. This is not very well preserved, right? We all agree on this one here. But some do. Some show just accumulation of shriveled up carbon that lines something that has morphology, sizes, orientation, like we know from modern microbial mats. So if we can then conclude, oh, those were cyanobacteria like the modern ones, I personally would say it could be. Oh, I mean, there needs to be done more work. Others might say, well, you know, those could have been just anoxic ones like Beggiatura. The problem is with Beggiatura with respect to morphology that they look like oscillatoria, same, you know, same organism, more or less, just a different metabolic activity. So that's really that depends on future work that could be done to decide. Here we have no cyanobacteria, but a microbial mat, which is whatever methanogenic bacteria that formed a thick microbial mat. Here it could be cyanobacteria, and they could have been even photoautotroph. I have nothing against to say they were photoautotroph, because of the large amount of EPS that was produced in those microbial mats. That requires a lot of energy. I'm not a microbiologist, so I better stop talking now. With respect to morphology and cyanobacteria, we need to be careful here, because what we see in the modern and probably also in the fossil, the morphologies are ecotypes. Ecotypes that must not represent the genotype of a microorganism.
But this spaghetti shape, is it individual cells or is it colonies of cyanobacteria?
I think those are organized into those bundles. Yeah.
Into colonies, yeah.
Yeah, in a way, yeah. So I'm very careful with saying colonies, because then some people might say, oh, that's already, you know, multicellular and all that. Yeah. So.
Yeah, but in addition to filamentous, there are coccoids which probably look more similar to what you see, right? Oh, that's would be examples of coccoids, yeah.
In the fossil, you mean?
Yeah, in the so for cyanobacteria we can see filamentous, but we can also see a sort of spherical, like a coccoidal shape.
I would have to look once more and really browse, but I have to be very honest. If I take a look at this here, where is it now? Jesus. You know, here. Well, you know, that's not the best example, but we do statistics with respect to orientation of something that could have been filaments. If you zoom in, we see something that, as far as I know, it's typical for a lot of early Archean cherts that include carbonaceous matter. That was described by Andy Knoll actually in the 80s already, that the organic, the carbon, the carbonaceous matter shrivels up, it shrinks. And what then happens is that we have little carbon dots. Gosh, where's my arrow now? Which you see here, lining what was originally a coherent filament, or could have been a coherent filament. If that happens to a coccoid cell somewhere here, see here you have little individual specks of carbon. These could have been coccoid ones, but really I would very be careful to say they were indeed coccoids, because it's just the preservation is so bad that we, being like spoiled by those photographs of people who work on real carbonaceous microfossils in chert, where we see beautifully preserved cells and all kinds of things. It's not like this, not in the material that I'm presenting here. So I would say it could be coccoids and filaments. It looks like, but you really can't say.
Thank you. Daryl has a question.
Yeah, is there any way of distinguishing microbial chips produced in these very shallow water environments and those produced on slope environments?
So if you say slope, of course, slope comes in different dimensions, right? You can have a continental slope, or you can have a slope in a tidal channel, or even at a ripple mark, right? So it really depends. Now, if we go into a ripple mark, let me do something here. I hope I find it quickly enough now. A ripple mark, I know exactly what I want to show you. This one here. If I find my arrow, yeah. So here, this is a ripple mark coming up, ripple valley, ripple crest, ripple valley. Here you see it's slightly pink in color where the crest is. See that?
Yep.
That is a slightly different population of microbes than here in the ripple valley, because here you have more, effects by oxygen and so forth. Here it's a little bit anoxic. Now, if we would go ahead and form a microbial mat chip, if the chip would form here, it would be a slightly different population in that chip as well, of different, like a chip that would form here. If we go now into a continental slope, and there is work done by Michael Tice and Maud Walsh down low from material in South Africa, there you have, we see things like roll-ups, microbial mats, but really there we don't really know where those mats originally came from somewhere, how high away. We would have to go and check out the points of origin of those chips that were transported several hundreds of meters, maybe even further. So in that case, we cannot make the connection to the origin where the chips come from. So yes, there are different types of mat chips that we know. In another presentation, I can show you chips made from epibenthic microbial mats versus chips made from endobenthic microbial mats. But as soon as we go into the fossil record and we are far away from the source of origin where the mats grew, it's difficult to make a connection and say, yeah, this was an endobenthic mat, so there was a tidal flat somewhere. I have to be very careful with that. I don't know whether I answered your question or whether I was drifting off.
Yeah, no, it's like dealing with things like, always have the sample handy. This is a 1340 thing from the Musca supergroup, and we got lots of little microchips in there.
Mm-hmm.
And other places where I've got very good sort of wrinkly, crinkly bedding. So I know there's been microbial mats of some form, but what I don't understand is how much compaction should I be looking at of the chips themselves, and were the distinctive shapes, like were these? Can I say some of these chips were derived from the shelf environments and then moved down to say 400 meters of water depth?
Yes, so if you have a very good understanding from the paleo environment, like Mike Tice and Don Lowe did, in a very detailed study, and Maud Walsh and colleagues, then you can see basically those roll-ups, and I just showed an example here. So what you see here is, first of all, you see there's, and I wish I would have a better photo of exactly this one here in this talk. You see there's a significant amount of sediment. Now this is clastic here, so this is grains, and you can't compress sand. Yeah, the sand grains, the quartz. If you like to compress quartz grains, so they really enter the grain boundaries would form a zigzag pattern. So like stylolites in carbonate. You can't do that in a sandstone unless you have metamorphic activity and pressure, enormous pressure, which is not the case here for the Dresser Formation, or maybe your environment where you're working. So the shape of chips that roll over is very, very solid. It's very well preserved, because you might compress the metal layer a little bit. It's just a dewatering process, but the organic matter is still there. So I would say to identify a mat chip in the fossil record, that's relatively clear cut, it is what it is. But to say, okay, good, this chip really derives from that particular mat that we see in higher areas of our nicely surveyed paleo environment, then I would say have to be a little bit careful, maybe with more sophisticated instrumentation that people have nowadays. Think of Kieron, Hickman Lewis, people like that. They might say, okay, we have similar microbes and chemical signatures, then maybe it's possible, yeah.
Okay, thank you.
Okay. Well, great. I think discussion has come to a close. Thank you so much, Nora, for presenting today. It's good to have you.
Yeah, thank you. I enjoyed the discussions and the presentation, and wish everybody the best. Stay healthy.
Yes.
Yeah.
Have a good one, everybody. See you around.
Bye.
Okay, bye.
Bye.